Okay, Haley, I'm going to try to work through page 495, number 5 for you. Now, this video is just for you, so it's not going to be professional quality. If I get confused, I'm just going to pause and keep going. So I'm going to try to draw this as best as I can, and I'm not very good at drawing the pulley stuff, but we've got M1 up here on a frictionless surface connected with a rope over a pulley to M2, which is hanging off the side. So we need to find three things, I guess: the acceleration of the system and the tension in both of the ropes. Now, it may not be obvious, and we haven't explicitly talked about this yet, but I'm going to call this T1 instead of FT1, just so it doesn't get crowded. There's the tension in that part of the rope. I'm going to call this T2. Now, they're different. They've been the same when we were talking about the massless, frictionless pulley back in the Atwood machine. We were ignoring the fact that it takes some force or some torque to actually rotate the pulley. So we are not ignoring that this time. So we're saying that M2 is going to exert that tension T2, and some of that is going to go into rotating the pulley, and the rest of it is going to go into T1. So just like we talked about something rolling down a hill, some of the energy goes into getting it down the hill, some of it goes into making it roll. The same thing is happening here. So T1 is not equal to T2, which I did write pretty large on the solutions, but if you don't understand why, then that's not helpful. That's why. Some of T2 goes into rotating the pulley, and then the rest of it is T1. So hopefully that helped that part. So let's write our Newton's second law formulas for both objects and for the pulley. So for block 1, well, there's no friction on that, so T1 goes to the right, nothing goes to the left, and so the net force is equal to M1 times acceleration. Now, they will accelerate. The string cannot stretch, so the acceleration is still going to be the same for both blocks. They won't have different accelerations, but like I said before, the tension will be different. Okay, so that was easy. How about our Newton's second law formula for block 2? All right, well, we know it's going to go down, so M2G is down, T2 is up, and that's going to equal M2A. So that is my second formula. Okay, then I need my Newton's second law for the pulley. So tau equals I alpha. And so what's the torque on the pulley? Well, T2 is going to make it rotate clockwise, but T1 is going to make it rotate counterclockwise. So okay, sorry, I stopped recording for a second and I'm not sure what I had said, but we're going to do the net torque on the pulley, right? Assuming that the pulley is rotating clockwise here. So T2 is going to tend to pull it down, right? So think of T2 as pulling M2 up, but pulling the pulley in the clockwise direction. Then we're going to have a minus T1. Think of T1 as pulling M1 to the right, but then making the pulley rotate in the opposite direction. So that's how we get the net force on the pulley. Then we multiply that by R to get the net torque on the pulley, and that's I alpha. So then I'm going to rewrite this. Let's call that equation number 1, that equation number 2. I'm going to rewrite this T2 minus T1 times R equals, now I'm going to use the rotational inertia of the disk, MPRP squared. And then instead of alpha here, I'm going to write A over R, okay? Because remember, that was one of our tricks. A equals alpha R, because everything I have for block 1 and block 2 is in terms of A. So I want to write this formula in terms of A as well, so that I can solve for A. So doing a little bit of algebra here, T2 minus T1, this R and one of these R's can cancel, and then this R and this R can cancel. So we get 1/2 the mass of the pulley times acceleration. I know that I've gone back and forth between R sub P and just R, but there's only one radius here, so I apologize for being a little sloppy there. So there's my three formulas, right? I've got T1 is equal to M1A, and then T2. I've got an expression for T2 there, and now I've got an expression for putting them together. So we really could do lots of different things, but what I'm going to do is substitute my expression for T1, and then let me quick do my expression for T2, which is M2G minus M2A. I'm going to just substitute those into this. So let me write this again, T2 minus T1 equals 1/2 the mass of the pulley times the acceleration. So my expression for T2, sorry, I keep there's my expression for T2, so I'm going to write that down. M2G minus M2A minus, now I need my expression for T1, which is a little easier right there. Whoops, too far. Minus M1A equals 1/2 the mass of the pulley times A. Okay, so now again, how many times have I said this? It's just algebra. It's a mess, but it's just algebra. M2G minus M2A minus M1A equals 1/2 MP times A. Remember, I am solving for A, so I want to get all my A terms together. So M2G equals 1/2 MPA plus M1A plus M2A. So let's factor 1/2. Here's that kind of annoying 1/2 the mass of the pulley, again, that keeps rearing its ugly head, plus M2 equals M2 times G. Now, I have all of this information, which I didn't write down, but it's in the book. So we know the mass of the pulley, we know the mass of the blocks, and so we get an acceleration of 6.27 meters per second squared. So that's kind of a long plug and chug. The tension in the two ropes then is quite easy to get because we know everything else. So T1 equals M1 times our acceleration, which gives us 12.5 newtons. T2, I know things are getting messy here. T2 is M2G minus M2A, and so we get 14 newtons there. And that, let's go back to what I said at the beginning. The tensions in the rope are not equal. It's true that the rope is still not stretching, but what it does have to do is it has to rotate the pulley. So this tension is 14 newtons. This tension is 12.5. Don't worry like how much it changed at this point. I'm not even sure if we'll be able to do that, but just the fact that they are different matters. Hopefully that helps you solve part A. Now, part B and C are really just kinematics equations. Part B says, how much time does it take for them to move a distance of 2.25 meters? Well, now we just have a system, and you can use either block, it doesn't matter. The initial velocity is 0, the delta x is 2.25 meters, and we just solved for the acceleration, which was 6.27 meters per second. So this was just, I'm not going to take your time to do the whole thing. I just used this formula. And it doesn't matter which block because the mass doesn't appear and the mass doesn't matter. So you get a time here of 0.85 seconds. Then they ask for the final angular speed. Okay, so they are going back and forth here, aren't they? So in order to find the final angular speed, we need the angular acceleration. Okay, but again, we know the angular acceleration is a over r. So it turns out to be 157 radians per second squared, which is not a small angular acceleration. So for this, I used omega f equals omega I plus alpha t, using the time that I got up here, and I got a final speed of 133 rads per second. So I know this was a long video. It's almost 10 minutes long. So I'm going to stop it. I'm going to let you watch it. And if you still have questions, feel free to email me back. Good luck.